person's maximum heart rate is the highest rate at which their heart beats during certain extreme kinds of exercise. It is measured in beats per minute, or BPM. It can be measured under controlled conditions. As part of a study in 2001, researchers measured the maximum heart rate of 514 adults and compared it to each person's age. The results were like those shown in the scatter plot below. So we have 514 dots here in the scatter plot, representing maximum heart rate and age in years of 514 adults in this experiment. So for example here, this dot here represents an adult whose age is found by projecting down onto the x-axis. We see that the age of this individual is between 18 and 20 years. Each of these dashes represent 2 years. So the age of this individual looks like 19 years approximately, and the maximum heart rate for this individual is about 172 to 173 beats per minute. We're going to consider the correlation coefficient of this data. We're not going to calculate it. Well, we can't, because we need to plug in 514 data values, XY pairs, into a formula or into a calculator, and we'd have to read them off from this, and we can't do that. That's not feasible. So we're only going to just estimate it just by looking at this. So I'm just going to give a chart of correlation coefficients from Wikipedia. We know that the correlation coefficient R is a number ranging from between -1 and +1. R gives a measure of linear dependence between the two variables. Linear dependence means how best can the data be modeled by a straight line. That's what's meant by linear dependence. As I explained in the previous video, if all the points lie on a straight line with positive slope, the correlation coefficient R is equal to 1. So this line has positive slope. If we take any point and increase x, y will increase by a certain amount. Here R is equal to 0.8. So here we have a strong linear positive correlation. Okay. Now our data, as you can see, has a negative correlation. We see that the line of best fit has negative slope. Now we don't have to worry about how to calculate that line in this course, but we can see that this data is probably best approximated by this example here. So we have a strong negative correlation. So as age increases, or as x increases, on average maximum heart rate tends to decrease. So the line of best fit has a negative slope. So it looks like an answer of -0.8 is probably pretty good, or maybe even a bit less than this, but not -0.4. I actually should say greater than this, because -0.4 is greater than -0.8, but I'm just talking about in absolute terms. The correlation here is less than the correlation here. So I would say it's not quite -0.8, maybe -0.7 or -0.75. I suppose if you give a value, say from -0.65 up to -0.8, that's a pretty good range. So that's fairly acceptable just from eyeballing this data. The next thing we want to consider is an outlier on this diagram. Now, an outlier, roughly speaking, is a point that's a long way from the bulk of the data. So you can see that this point is actually quite a distance from the bulk of the data. So really, this is the best example of an outlier in this data. You might say this point up here is an outlier, but it's not as far away from the bulk of the data as this particular value is. So let's write down age and maximum heart rate for the person represented by this point. Coordinates of this point here look to me to be 46, 137. So age is 46 years, and maximum heart rate, maximum BPM, for an extreme form of exercise in this experiment is 137 beats per minute. Another good approximation might be 47,137. Now we're going to consider the maximum heart rate in BPMs of a 47-year-old. We're going to do that by using the line of best fit. So we go to 47, which is about here, and we just project up to the line. So this is just a pretty rough estimate. I'm not doing this too accurately, but I appear to have an answer here of 172, 174. Each of these dashes represents 2 units, or 2 BPMs. So we have 170, 172, 174 beats per minute. Let's do the same calculation for a 44-year-old. So 44 is here, so we just go up to the line, and if we go across from there, we get an answer of 176. So for a 44-year-old, we have a maximum BPM of 176. So we have the point 44, 176, this point on the line. So we're using the line of best fit to do these calculations. Now we're going to consider the slope of the line of best fit. To do that, we just need to pick 2 points on the line. So here I'm looking at an x value of 10. It's a person aged 10 years, and I'm going up to the line. We can extrapolate this line. We can just extend it on here, and it appears that the point 10, 200 is on the line. Okay, the origin here is not at 0. The origin is at x equals 10. And if we project up to the line, we have to extend it a bit. It looks like y value is 200. So we have this point here, coordinates 10, 200. I've picked another value here when x is 90. That's the most extreme value actually. And we can continue this line on, and we can try and read off the y value of this point here, which is about here, which is that's 144. Each of these dashes is 2 beats per minute. So this point here is coordinates 90, 144. This is 10, 200. And how do we get the slope of a line? Well, we just get the vertical distances between these 2 points. That's this distance here. We just subtract the y values. That's 200 minus 144. We have 156 here. And then we get the horizontal distance. This is between the 2 points. We just subtract the x values. That's 90 minus 10. That's 80. So the slope of the line is this distance is also y2 minus y1, and this distance here is x2 minus x1. So it's y2 minus y1 over x2 minus x1. That's the slope of a line. So we have 56 over 80. Now this is the magnitude of the slope of the line, but we realize that this line has negative slope. So we stick a minus sign in here. So we get a line with a slope of minus 0.7. Why does it have a negative slope? Well, if we pick any point on the line and increase x by 1 unit, 1 unit is going to look very small in this scale here. It's one of these units. If we increase x by 1 unit, then y will actually decrease. We'll have to go down to meet the line. So when we have to go down to meet the line after increasing x by 1, the slope will be negative. And the distance that we go down by will be 0.7, so it's too small to show on this diagram. But if I enlarge it, if we imagine increasing x by 1, we'd be decreasing y by 0.7. That's the idea. And this number is the slope. And it's because we're decreasing y, we use a minus sign. The other way to do this is just to use the formula y2 minus y1 over x2 minus x1. So we label one point x1, y1 and the other point x2, y2. So the slope is y2 minus y1 over x2 minus x1, and if we plug all the values into this, we'll get out minus 0.7. Now let's consider the equation of the line of best fit. Now remember, we didn't actually calculate the line of best fit by using all the coordinates of the points, that's 514. There is a formula for doing that. This line is known as the least squares line, but that's not on the course. And anyway, to do this for this data would be impractical. We'd have to use a computer because there's just far too many points. We're only doing this by eyeballing the data, and well, the line is actually shown in the data, and we got the slope, and now we want to get the equation. So we pick 2 points on the line just by looking at the diagram. And we got we got the slope. So what we want to do now is just get the equation. So to get the equation of a line, we need 1 point on the line and the slope of the line. And we have our formula y minus y1 equals m times x minus x1. So that should be familiar. And if I rearrange that, I get y equals minus 0.7x plus 207. Now, what is y and what is x? What are the variables? Well, the y-axis is the maximum heart rate. So I can write MHR for maximum heart rate. And the x-axis is the age of each of the adults. So I can write my equation as MHR equals minus 0.7 times age plus 207. The researchers compared their new rule for estimating maximum heart rate to an older rule. The older rule is maximum heart rate equals 220 minus age. The two rules can give different estimates of a person's maximum heart rate. Describe how the level of agreement between the two rules varies according to the age of the person. Illustrate your answer with 2 examples. So here's the old rule. MHR equals 220 minus age. I can just write that down as y equals 220 minus x. So that's different from our new rule. Our new rule we calculated in the previous part was y equals minus 0.7x plus 202, I think. I'll just note that. So here's the new rule. I'm just writing y for MHR and x for age. It's just easier to read it now. And I've just written this new rule slightly differently. I've written the constant term first and the x term second, but it doesn't really matter. So what we want to do is compare these two rules, and we're going to consider how they vary for the age of a person. So we're going to consider a young person and an old person as two extremes. So I'll just do the old rule in this color here. The old rule, say for a person aged 10. So if I plug 10 into this, I get 220 minus 10. That's 210. So we have the point 10, comma 210. So that's 1 point on our old rule. So our old rule is just going to be a straight line. This is the equation of a straight line. So this is a point on that line. And we can pick a second point on this line. We could just take another value down here. Well, we could actually take any value for the age, but I'm going to just plug in 90. X equals 90 gives y equals 220 minus 90, which is 130. So we have the point 90, comma 130. So 90, 130 is here. And we just join this point to this point here, and that gives us the old rule. That's the old relationship, or the old line of best fit, if you like, between maximum heart rate and age. Well, actually, it won't be the best fit for this data. It's just a rule inferred from other principles. It's not a line of best fit for this data. The line of best fit for this data here is what we call our new rule. So we can see that for young adults, our old rule gives a greater MHR than the new rule. Okay, say for an adult age 20, our old rule gives an MHR of this value here, whatever that is. It's more than 200, but it's greater than the corresponding MHR in our new rule. Okay, so for a young adult, we get a greater MHR in the old rule than for the new rule, but the opposite is the case for an old adult. So say for an adult aged 80, we see that our old rule gives a lower maximum heart rate for extreme exercise than our new rule. But there's good agreement around here between the two rules. So for an adult age 50, both rules give approximately the same value of MHR, the same maximum heart rate. A particular exercise program is based on the idea that a person will get most benefit by exercising at 75% of their estimated maximum heart rate. A 65-year-old man has been following this program using the old rule for estimating MHR. If he learns about the researcher's new rule for estimating MHR, how should he change what he is doing? So let's see what 75% of MHR is for a 65-year-old man using the old rule. So his age is 65, that's X. So the maximum heart rate is going to be Y, which is going to be 220 minus 65. So here's the old rule, I'm just doing it in brown. And the exercise program says that the person will get most benefit by exercising at 75% of this. So we're going to get 75% of the maximum heart rate for a 65-year-old man. So we just get 75% of 155. So that's 0.75 multiplied by 155. That's 116 beats per minute. Now, I'll do the same thing for the new rule. So X is 65 and the maximum heart rate in the new rule is Y equals 207 minus 0.7 times X, which is 65. That's 161.5, and the recommendation is to do 75% of the maximum heart rate, so we get 75% of this number. That's 121.125 beats per minute. So you can see that under the new rule, that's all of this here, he has to exercise more intensely. He has to get his heartbeat from 116 beats per minute up to 121.125 beats per minute. This is the new recommendation.